All right, Chapter 2, Section 7, Derivatives and Rates of Change. So finally in this section, we're going to formalize our definition of a derivative. But before we get to that, we're going to back up a little bit and begin with tangents. So first, we're going to go back and talk about tangent lines to a function at a point. We've mentioned them a little bit in the past, but we're going to come back and talk about those again. Then we're going to go back to our velocity problem again. Then we're going to formalize our definition of derivatives and finally visit rates of change. And what you'll notice throughout all of these is that there's a lot of similarities. In fact, they're all the same. The notation changes a little bit, the language, the vocabulary changes a little bit, but they're all the same thing. It's going to feel like Groundhog Day here, where I keep repeating myself with just slightly different variables. And that's really the point, to really drive home that they're all connected. They're all different ways of expressing the exact same thing. Okay, so first, let's go over to Desmos, where I want to revisit the idea of a tangent line at a point, how we find it, what it means, and then formalize a definition for it. And then we'll move on to an exercise involving velocities, displacement velocity functions, and then we'll move on to derivatives, and we'll cap it off with rates of change. Okay, so here on Desmos, I've typed in this equation, x cubed minus x plus 2. And then I'm also using this table here where I've typed in the same formula. And so this will be a table where I input some particular value of x, and then it'll automatically calculate it. So for example, if I type in a 0, then it'll automatically calculate 0 cubed minus 0 plus 2, which in this case is obviously 2. Once I have that relationship between the input-output, I can create an ordered pair that can be graphed. So here is the point 0, 2, right? So we can try different values. How about 1? How about 2? How about 3? Well, 3 already jumps to 26. I have to scoot up. Okay, so here's a few dots there. It doesn't have to be exclusively whole numbers. I can also put in decimals, of course, 1.2 or 2.7. Okay, well, eventually, if I keep graphing ordered pairs, I'll get a smooth curve that looks like this. And so this blue curvature here, this graph, is the result of graphing an infinite number of input-output pairs, right? So this equation establishes a relationship between the input x variable and the output y variable. So that relationship is very valuable. We get a lot of information out of it, but there's a lot of stuff missing. So for example, let's concentrate on a couple of input-output pairs. So let's say, for example, or note that if I put in -1, the output is 2. There it is. If I put in 0, the output is also 2. There it is. And if I put in 1, the output is also 2. Here is 3 different inputs, 3 different input values that result in the exact same output value of 2. Let me zoom into here for a little bit. Okay, so I zoomed into there for a little bit. Okay, so here is -1, 2, 0, 2, and 1, 2. All 3 input values give you the same output. And that's very valuable information, but we'd like to know more. One of the things we'd like to know is when the input value is 1, the output is 2, but where is it heading? I can see from my picture that the graph is heading up, right? As I input other values that are slightly bigger than 1, I can expect my output to be slightly bigger than 2. Right? I can see that from my picture. I can see that when the input value is 0, the graph is slightly decreasing beyond that. I can expect that another input value that's really close to 0 but a little bit larger is probably going to be a little bit smaller than 2, right? And likewise over here in -1, I can see when the input value is -1, the output is 2, but I can expect that if I input another value that's really close to -1, but slightly to the right of it, in other words, a little bit closer to 0, then the output value I expect would be a little bit bigger than 2. So at -1, the output is 2, but increasing. At 0, the output is 2, but decreasing. And at 1, the output is 2, but increasing. I can see that from my picture. But what if the picture is not there, right? If we just have those 3 input-output pairs, then we have no more information, right? I would like more information. I would like to know what happens next. And of course, well, one way you could do that is just to put a graph and say, here, look at it. But that's not good enough because we want to quantify it, right? How sharply of an increase is it? At when the input is 1, the output is 2, I can see that it's increasing. At -1, the output is 2. I can also see that it's increasing, right? But is this increase, how does that increase there compared to the increase there? Is one sharper than the other? I would like a number. I would like to quantify it. I would like an equation, something to solidify how it's changing at that point. Okay, so how are we going to do that? Let's focus our attention on just one of these points. And for the purposes of this, I want to work with 2. So 2 leads to, let's come back over here, 2 leads to 8. And I can see that it's increasing. And it looks like a very sharp increase. But graphs can be deceiving. So I'm going to change the scale of my graph to kind of flatten it out a little bit more, giving myself more room to work with. And you'll see that, among other things, one of the things you'll notice is that the picture can be deceiving. That's why we want to rely on a number, on an equation, on something a little more algebraic, rather than saying, oh, the picture told me that it's going up sharply at this point. Okay? All right, so let's change the scale. Okay, so now that I changed the scale, here is the input-output pair at 2, 2, 8. And now it doesn't look quite as sharp of an increase from the picture anymore, right? And then earlier when we were looking at the input-output pair of 1, 2, it looked like it was sharply increasing beyond that, and now it looks a little bit more flat, right? Likewise, at 0, 2, before it looked like it was decreasing. Now it almost looks like it's pretty flat there, right? So pictures can be deceiving. That's why we're looking for a more algebraic description of how it's changing at a particular point. Okay, so we have the input-output pair 2, 8. At this point, the input is 2, the output is 8, but we want to know where is it heading beyond that. How are we going to get a good approximation to that? Well, for one thing, we're going to start off by considering another ordered pair that's also on the curvature that's relatively close to 2. And we'll stick to a number to the right of it for this purpose. So let's consider the point 4, 8, another point on the curvature, 2 units to the right of the one I'm interested. Keep an eye on this one. This is the one I'm interested in for the purposes of this demo here. I'm interested in knowing what is happening at this output pair, at this input-output pair. Where is the graph heading next? So one thing we could do is find another point, find the line that connects those 2 points, and then we can get a good sense of where this is going based on that. So if we connect this point and that point together, we'll get this line. It goes through this ordered pair and this ordered pair. So now we can find the slope of this green line by finding the change in the y-axis direction and the change in the x-axis direction. Divide those 2 things together and we'll get the slope of this green line. So the change in the y-axis direction is going to be the difference between this output, which was 62, the result of the 4. So notation-wise, we like to write f of 4. That's equal to that 62. And then subtract away this, which is the result of inputting 2 into our function. So that would be minus f of 2. So that'll really be equal to 62 minus 8. this one is, which equals to 54. Okay, so this change in this direction is 54. And then in this direction, we see that this is really just going to be a 2. It's the 4 minus 2, which then equals to just 2. So if I divide these two things together, I get the slope of the green line. So green line is m equals 2. And then just to kind of formalize it again into the formula, it's f of 4 minus f of 2 divided by 4 minus 2, which gives you m equals to 54 divided by 2, which gives you 27. So the slope of this green line right here, m equals to 27. Remember, slope is rise over run. Slope is rise over run. It's a description of the steepness of that green line. So it's a pretty good indication of what's happening at this point. If we had to guess, when the input is 2, the output is 8, and it's increasing, and a good guess for how that increase, or the quantity of that increase, would be the slope of the green one, which at this point would be 27 or 27 over 1. Right? We can interpret that as rise over run, 27 units for each unit, each 1 unit in the horizontal, 27 units in the rise. Okay, but we could do better. So let's go back to Desmos. Okay, so back to Desmos. So we figured out that the slope of this green one is 27. So that gives us a pretty good indication of the steepness of this green line, which is a pretty good indication of what's happening at this point. So when the input is 2, the output is 8, and a slope of 27 gives us a pretty good idea of how this is increasing. At what rate is it increasing? My best guess at this point is 27 units, right? So that's a number that describes the steepness of this line. It's a number that describes how sharply this point is increasing at this point on my function. Okay, it's a pretty good guess, but we could do better. So let's graph the point. Okay, so here is my input point. The input value of 4 is what we were just working with. So let's scoot this a little bit closer. Let's make the interval here a little bit smaller. Remember, keep your eye on 2, 8. That's what we're interested in. So if we scoot this point a little bit closer, as we scoot it closer, we see that the ordered pair along the f of x curvature gets a little closer to this one. So we scoot it up, scoot it up, scoot it up. Let's bring it down to 3.5. So at this point, at 3.5, we're a little bit closer to this point. We can draw the line that connects those two. And now, once again, we can figure out this newfound slope. At the input value of 3.5, the output value is 41.375. So we can figure out that slope. Okay, so we had already previously calculated that the slope of this line was 27. Right? And that was a pretty good estimation of what's happening at this point. The input is 2, the output is 8, and how fast is it increasing? Well, we can quantify it and say 27. 27 is a way of describing the steepness of this line. Right? 27 lets you know roughly that for every 1 unit in this direction, we go up by 27 units. So that's just an estimation. But we could do better, so we decided to scoot this guy over from 4 over to 3.5, and we get this. So now we can find the newfound slope here. Okay, so we can create the triangle that's formed underneath. We know that if we want to find this, this is f of 3.5 minus f of 2. Keep your eye on the ball. The book calls this point P, right? So that's the one we're interested in, figuring out a way of describing what's happening at this point. So this is f of 3.5 minus f of 2. We can see from our from our Desmos graph that this output is this decimal. So that's going to be 41.375 minus 8, which equals to 33.375. This is the change in the y-axis direction. And then in this direction, we can see that it's 3.5 minus 2, which is equal to 1.5. Okay, so then the slope, m, of this new graph is equal to f of 3.5 minus f of 2 all over 3.5 minus 2. So we get m equals to 33.375 divided by 1.5, which means m equals to 22.25. 22.25. Okay, so that's the slope of this second line. So now m here equals to 22.25. So we have a new approximation for what is happening, the change, the rise that is happening at this point. So we can say the input is 2, the output is 8 at this point in our curvature, and I know it's increasing, and the best way to describe how that increase is happening is by this slope of 22.25, where each 1 unit in this direction, I expect a rise of about 22.25 units, right? So it's just an indication, an approximation of how this point is rising at this value. Okay, well, you can see where we're heading here. We're going to get closer and closer and closer. So let's go back to Desmos. Okay, so we found that this slope was 27. The slope of this line was 22.25. It's a better approximation. And then, of course, if we want an even better approximation, we want to scoot this point even closer. So let's scoot it from 3.5 over to 3. And we get 2 new points along the curvature. Remember, this is the point of interest. This is point P. We want to know what's happening at this point. So we're going to look at this point. Your book calls it Q, which is relatively close. Now we're much, much closer. And we see that at this point, we have another point on the curvature. We draw a new line. We can find this new slope. Okay, so now we're going to find this new slope. We can come up with the little triangle that forms underneath that green line from there to there using these. So your book calls this point P, the point of interest, and then they call this point Q, the other point that we find. Okay, so now the slope of this new green line is going to be this. It's going to be f of 3 minus f of 2. Right? The output at 3, which we can see from our graph here that this is a 26 and that this is still that 8. So this is going to be equal to 18. And then in this direction, it's just a nice change of 1. So now this new slope here, m, is going to be equal to f of 3 minus f of 2 all over 3 minus 2, which means m equals to 26 minus 8 divided by 1, which means m equals to 18. We found the new slope. Okay, so way back over here, we found that when we use this point, 4, 62, and 2, 8, when we found that first gas, we saw that its slope was m equals to 27. And then we got a better approximation by using this, when we used the input pair of 3.5, and then we saw that this m was 22.25. And now, after this work, we see that this new m equals to 18. So we see that the slope is getting smaller. It's still positive. Okay, so we see that we started off with an approximation of 27. If you said, okay, the input is 2, the output is 8, how fast is it rising? Our best guess would have been 27 at this starting point, right? For 1 unit this way, we would have expected to rise 27 units from there. Okay, but then we got a better approximation by moving this point a little closer, making the interval in the domain a little bit smaller. And so we saw that the next time we calculated the slope, it was 22.25. That's a better guess. And then this third time around, we see that the slope is 18, meaning that for 1 unit in this direction, we expect a rise of about 18. And we can see that does do a pretty good job of approximating things. But okay, so what we're going to do is get closer and closer and closer and closer and closer. I could go through the work of figuring out at 2.5, or at 2.2, or at 2.1, or at 2.01, or at 2.001, right? We want to get really, really, really close. And the closer we get, the better the approximation is going to be. So let's see what it looks like on Desmos. So there it is. So remember, this slope over here was 27. The slope of this one was 22.25, and we just found the slope of this one to be 18. But now we want to get even closer, so we're going to scoot this even closer. We can go over to 2.5, and we can figure out that slope. I'm not going to do that. I think you can see how we can find that if we wanted to. So that's what it would look like when the input value is 2.5, and then we get even closer and even closer and even closer and even closer and even closer. Okay, so what we're going to do is we're going to set up a limit where we just find the slope of the green one in general, and then we're going to let the limit as this input value gets infinitely close to the target value, and if that limit exists, that'll give us a slope of two lines, of the slope of the line that connects 2 points that are infinitely close to each other, and that is what we're going to consider to be the slope of a line that is tangent. Okay, so what does it look like? It looks like this. Okay, remember, our goal is to get a sense of where it's heading at this point. The input's 2, the output's 8, but where is it heading? So we initially got a slope of 27, and then as this got closer and closer and closer, we got different approximations. And then as we let this gap get infinitely small, as these 2 points get infinitely close to each other, as the space between them grows to 0, the limit as this input value here grows toward 2, then the resulting green lines will have a slope that's getting closer and closer and closer to what we consider the tangent line. Okay, so the tangent line, which is in red here, will be a line that touches our graph at exactly 1 point and has a slope that gives us a pretty good idea of where is it heading next, and it'll be a slope that is found by finding the slope of the line that connects 2 arbitrarily selected points on curvature, and then figuring out the limit of that slope as they get infinitely close to each other. Okay, so let's look at the. Okay, let's. It's a little messy, so let's get rid of some of these things. Okay, so remember that the blue one is our original function f of x, and then we are interested in finding information about where is it heading beyond this point. What is the instantaneous rate of change at this point? Is it an output of 8, but it's increasing, decreasing? What is it doing? And so that's what this tangent line will do for us. It's a line that touches our curvature at exactly the point we're interested in, the point 2, 8 in this little example, and also whose slope gives us information about how this function is moving, where is it heading next. So we want that slope to be approximated by the slope of these other secant lines. So I started by letting a second point that's relatively close. This point, 2, 62. We can find the slope of that line, and then as this x equals to 4 gets closer and closer and closer, as I'm getting closer to my target point of 2, as I get closer and closer and closer, as this value increases that way, as this gap gets smaller, then this point, the resulting point on the curvature, will grow along the curvature to get to this point, and the resulting lines that are created between this point and this point, if we find the slopes of those, that's easy because there's 2 points, then eventually we see that they get really, 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 really close. The slope of the green one gets really close to the slope of the red one. Okay, so let's see a more formal definition of all this. Hopefully that made a little sense. Let's see how this works. If a curve C has equations y equals to f of x, and we want to find the tangent line to C at a point P, which is a comma f of a, then we consider a nearby point Q with coordinate pairs x comma f of x, where x does not equal to a, and compute the slope of the secant line PQ. Okay, so those would be all those green lines I was just pointing at. And those can easily be found by this ratio, f of x minus f of a all over x minus a. This numerator is going to be the change in the y-axis direction, the change in the outputs, and the denominator is going to be change in the x-axis direction. Okay, and then we let q approach p along the curvature c by letting x approach a. Okay, what is all that? Well, we have some nice little pictures of that. Same thing. So here we have a a picture describing what I was trying to do. So we have a function. This black one here is my function f of x, and we have a point A that is in the domain of my function. It leads to some output f of a. So we're going to let this point right here be point A. That's the point of interest. I'm interested in finding out what's happening to my function at this point. What is the instantaneous rate of change going to be? So in order to figure that out, what we're going to do is, what we're going to do is we're going to think about some other point that's not equal to a, some other input value not equal to a. In this case, let's just say x, ideally close to a. And then we get another output. We're going to call that q. That's going to be x comma f of x. We're going to draw the line that connects those two. We're going to find the slope of this secant line. The slope of this secant line is easy to calculate because we do have 2 points. These are ordered pairs. So if we calculate the difference between this output and that output, we get this. This is the change in the y direction. This is also known as the rise, or the change in the y-axis direction, whereas this is known as the change in the x-axis direction, also known as the run, if you remember it that way. This would be the run. And then we know that the slope of that blue line is equal to rise over run, which is going to be equal to this divided by this. Okay, so this formula right here will give you the slope of that blue line right there. And now the point is that we're going to start moving our x value. We keep the a constant. We don't let that change at all. And we're going to let this x value get closer and closer and closer to a. And as x gets closer to a, its resulting output q value will slide closer and closer and closer to the p value along that curvature. And as it gets closer and closer and closer to p, the new resulting lines that connect the point P and Q will have new slopes that become a closer and closer approximation to describing what's happening at P. What is the instantaneous rate of change at P? Okay, so here's another little visual. So if we have Q starting off here at some x value, and we have some value here, as we slide x closer and closer to A, the values of q along the curvature travel along that curvature, and every time they get closer and closer and closer to p, we will have a new secant line whose slope becomes closer and closer and closer to this red one. That red one is what we call the tangent line. So this is the tangent line of our function f of x at point a comma f of a. which was point P, at point P equal to a comma f of a. Okay, so the slope of that red line is letting me know that it's a positive slope, it's rising, and I have a numerical quantity to describe how steep that rise is. It looks like a pretty solid steep rise. So for example, this f of x function could be unemployment rate. And I can see, okay, well, the unemployment rate is at this height, but beyond just telling me what the current unemployment rate is at an input value of a, we can also see where it's heading. Not only is it at this point, but it's on its way up. That's not good. On the other hand, maybe at this point, you go, okay, well, the unemployment rate, it's actually higher than it used to be, but it's on its way down, so maybe would be a little bit happier then. So there's a lot of information that we can get by knowing the direction in which the graph is heading next, which we call the instantaneous rate of change at a particular point. Okay, so hopefully that made sense. Okay, definition. The tangent line to the curve y equals to f of x at the point p equal to a f of a is the line through point P with slope equal to m, where m is equal to the limit as x approaches to a of f of x minus f of a all over x minus a, provided that the limit exists. Okay, so this, as we just saw a second ago, this is the slope between the point a comma f of a and some other point x comma f of x. Presumably the x and the a are somewhat close to each other along the domain of the function, but very crucially, x does not ever actually equal to a. It's just really, really close to a. So as we move the x closer and closer and closer to a, the gap between the two gets smaller, and so the slope of the secant lines gets closer and closer and closer to what we consider the tangent line. So a tangent line is a line. So the tangent line at point a comma f of a is a line that goes through the point a comma f of a and has exactly this slope, provided that it exists. Okay, find the equation of the tangent line to f of x equals to 5x minus x squared when x equals to 2. Okay, so the first thing we want to do is find the input-output relationship of this function when x equals to 2. So we're going to find f of 2. F of 2 equals 2. Okay, so the ordered pair 2 comma 6 is where we're interested. In the previous theorem, then this would be the point P. P equals to this. Okay, so now what we're going to do is think of a new point, a new value in the domain of this function that's close to the value 2. And then we want to find the formula that gives you that slope. Okay, the slope of the line that connects those 2 points. Okay, let's graph this equation. Okay, so here's my equation. It's this parabola looking thing. And I know that when the input is 2, the output is 6, so we have that point right there. And we're interested in finding the tangent line. So according to the definition, the tangent line is going to be a line that has this point, that goes through this point, and has a slope that is equal to the limit as x approaches to a of f of x minus f of a all over x minus a. So let's follow that formula to find the slope of the tangent line. Slope of the tangent line is going to be equal to m, which is equal to the limit as x approaches to 2, so in our case the a is the 2, of f of x minus f of 2 all over x minus 2, right? And this is where we're letting a equal to 2 for in this particular case. Okay, so now we have to evaluate our function at x. Well, that's just going to be copying it, really. So this will be the limit as x approaches to 2 of, And I want to distinguish between the two by introducing these parentheses here. So it's the first function minus the second function. Very important to keep that in mind because this subtraction applies to this entire function. And in the denominator, we're just going to have x minus 2. Okay, so for this first function, we're going to evaluate it at x. So let's put an x right in there. And put an x right in there, right? It is unfortunate that we keep recycling the same letter x, right? So really, ideally, this would be some other letter, but it looks a little confusing because this is f of x, and then we have an x there, but okay, so we're evaluating at x, so it means really we're just copying it down. And then the second one here, we're evaluating this one at 2. So let's put a 2 here, 2 there, and a 2 there. Okay, so now our goal is to simplify this using our rules of limits to figure out what this limit is, if it exists, and then that will be the slope, m, of the tangent line with this point, and then we can use those two pieces of information to find the equation of the tangent line. Okay, so next we're going to simplify this a little bit more. The limit as x approaches to 2, and well, this is just going to be 5x minus x squared minus, and then this is 10 minus 4, which is going to be 6, x minus 2, which is equal to the limit as x approaches to 2 of 5x minus x squared minus 6 all over x minus 2. Is equal to the limit as x approaches to 2. And I'm going to move this around so I can factor it, and I'm going to rewrite it as minus x squared plus 5x minus 6 divided by x minus 2. And then I'm going to factor out that negative 1. Now we see that this factors nicely. X times x is x squared, x times minus 3 is negative x, negative 2 times x is minus 5x, and negative 2 times negative 3 gives you positive 6. Okay, and now these two will cancel following our rules of limits, and we see that the only thing that survives is negative 1 times x minus 3. Okay, and then we can just distribute that. And we know that this is just a polynomial now. And from our work with limits, we know that whenever you evaluate a polynomial, then the limit is equivalent to just evaluating the polynomial at that point. So at this stage, we are done. This is going to be minus blank plus 3. And all we have to do is put a 2 right in there. And so after all that work, I see that my slope is equal to 1. Okay, so the tangent line is going to be a line that goes to the point 2, 6. So far I have that my tangent line is going to be a line that goes through the point 2, 6 because of this, and has slope of 1 from this formula. And now I can find the actual formula of my tangent line by using the formula y minus y sub given is equal to the slope times x minus x sub given, where the so this is the equation of a line where we know the slope. Here it is. So all we have to do is insert this guy into here. The slope goes into there. And some other given point, and this is the other given point on my line, so that'll be the x given and the y given. So all we have to do is replace those values onto here. This is going to be y minus 6 is equal to 1 times x minus 2. And then we distribute the 1, well, that's just going to be x minus 2. We get y minus 6 equals to x minus 2. And then bring the 6 over by adding 6 to both sides, plus 6, And so we get that y equals to x plus 4. Okay? So this is the equation of the line tangent. Okay? As a rough sketch here, we have our function looks a little something like this. And somewhere over here is the point 2, 6. And the line tangent is going to be something that looks like this. It goes there. And let's pretend that's a straight line. So there's a little point right there. The point that it touches, that's the point 2, 6. And I know that it goes through the point 0, 4 because that's its y-intercept. It's got a slope of, so this is tangent line, y equals to x plus 4. It's got a slope of 1, so right there, slope equal to 1. And this guy lets me know that the y-intercept is going to be the point 0, 4. So I know that this point right over there is the point 0, 4. Let's go back to Desmos and get an even better picture of this. Okay, so if this was our function here, f of x, then this would be the point we're interested at 2, 6. And we can use Desmos to find the tangent line at various points. So that could be found this way. And so at various points, we can see that these are the various tangent lines. Okay, and we're interested in the tangent line at the point 2, 6. So this is the one we're interested in. We want to find that equation. Okay, so we found that it was equal to y equals to x plus 4. And that confirms for us that in fact this purple line is that tangent line. It is that tangent line there. So that's the tangent line we're interested in. And we find it by, first of all, picking a starting point away from the number 2. Say, for example, 4. That leads to a point that's on my curvature. And we find the slope of that line. And then as that input value gets closer and closer and closer to 2, as it gets closer and closer and closer to 2, this output value, we can find the slope between these two. And as they get closer and closer and closer and closer, the slope of that green one gets infinitely close to the slope of the purple one. When we let the limit as x approaches to 2, that's what we found. That was the work we found right here. This whole limit thing is finding what the slope of that green one is going to be as the x value gets infinitely close to 2. This describes the slope of the tangent line. Okay, so this is a very common question you might be asked, to find the equation of a tangent line to a function at a given point. So remember that to do that, you first of all have to find the value, the point on the curvature that you're interested in. And next, you're going to have to find the slope of the tangent line. And this is the setup you need to do in order to find the slope of the tangent line. And then we use our rules of limits that we've learned in this chapter to find that limit if it exists. And once you find that value, you have the slope of the tangent line, and you'll have a point. And together we'll be able to use this formula to find the equation of the tangent line. All right, moving on. Okay, so we saw earlier that if we're trying to find the slope of the line that is tangent, we could use this notation style, where we're interested in the tangent line that goes through the point a comma f of a. And then so to do that, we think of a new point, x, and then we consider what happens as x approaches to a. But we also want to introduce a new style notation to achieve the exact same thing. But instead of calling this new point x, what we're going to do is we're going to call it a plus h, where h represents the gap between the two. Okay, so we've seen that before. and it'll look like this. So instead of having x, we'll have a and then a plus h, where the gap between those two input values is h. Therefore, this is still going to be the point p equal to a comma f of a. But this point now, instead of calling it x f of x, is going to be a plus h, that's the input, comma, f of a plus h. Right? So it's just a new kind of notation. This part here is now what used to be referred to as the x. Right? We used to call it x, some x value. So we used to have x here. And then therefore this would translate to some f of x. So we'd have point x comma f of x before. But we want to get away from this notation and introduce this notation, which primarily focuses on h, the gap between the two. So with this newfound notation, that means that the change in the y direction between these 2 points, right? So we have the point P, we have the point Q, and we want to be able to identify the line that connects them, and then we want to find the slope of the blue line. The slope of the blue line is going to be this, m sub pq. It's the slope of the secant line between point P and point Q. We've seen this before. So earlier, our formula was f of x minus f of a all over x minus a. That used to be the slope of the secant line. But now, because we're replacing the x with this a plus h, all we're going to do is come in here, replace the a plus h for x, and then this is what we get. Note that in the denominator, if we replace this x with a plus h, and then we subtract a, the a's cancel, we're left with just h, and that's why there's just an h in the denominator. It simplifies the denominator. In the numerator, instead of f of x, we have f of a plus h. So it's the exact same thing as before, just a slightly different notational style. So just like before, what we're going to do is we're interested in pushing this closer to a. So earlier, we were interested in finding the limit as x approaches to a, where this was our x, and we were pushing it closer and closer to a. And that would result in this output value, point Q, to get closer and closer and closer to P. Right? That's what we were doing earlier. So as, meaning that as x approached A, we saw that point Q was approaching point P, and again, the point was that the slope of the blue one was getting closer and closer and closer to being the slope of that red one, which is what we wanted. Now that we introduced this new notational style, we're not going to say let x get closer to A. What instead what we're going to do is we're going to think about letting h go to 0. The limit as h goes to 0. As the gap between the two gets smaller and smaller, as this happens, as h goes to 0, what happens is that the gap between these two gets smaller. It means that a plus h, that number, is approaching a, just like before, because the gap is getting smaller, which again means that q is approaching p. So they accomplish the same thing. The limit as x grows to a in this notation is the same thing as saying the limit as h goes to 0. It just simplifies things a little bit over here. Okay, so hopefully that change is manageable. Okay, so given this new notational style, we have a new formula for m, the slope of the tangent line. So let's do an example using this formula. So find the equation of the tangent line to function f of x equals to 2 over x plus 3 when x equals to 1. Okay, so step 1 is going to be to evaluate this function at x equals to 1, figure out its corresponding output. That'll be a point on our curvature that we're interested in, and also it'll be a point on the tangent line, the only point we can find out at this point. Okay, so We're going to evaluate this at 1 as requested. And so we get that f of 1 leads to 1/2, so we have the ordered pair 1 comma 1/2. Okay. Next, we need to find the slope of this tangent line using our new formula. So the slope of the tangent line m has a couple of different formulas we can use. So one of them was the one we used earlier. M is equal to the limit as x approaches to a of f of x minus f of a all over x minus a. That's one form of it. For us, a equals to 1. So, or m equals to the limit as x approaches to 1 of f of x minus f of 1 divided by x minus 1. Okay, so this is the formula that we used before, but now we're going to use this new style where we let h be the gap between the point of interest a equals to 1 and the new chosen value. Okay, so we're going to let m, the same slope of the tangent line, is equal to the limit as h approaches to 0 of f of x plus h minus f of x all over h. And for us, this time, the x is the constant. That's, we keep recycling x all the time. Here, in this style, note, this causes some confusion. So here, the m is the one that moves, right? So, here the x is the one that moves. So we have our value of interest. We have our point of interest a, which is going to be some point along my curvature there. So this leads to a comma f of a. That's the point I'm interested in. And so what we do is we grab this new x value and we slide it over, right? So x is the variable in this notation style. Whereas over here in this notation style, it is not the variable. X is the constant. H is the variable. So we have this. We have some sort of a function. Maybe it does that. And then we have some value a. Maybe it leads to there. So we're interested in the tangent line at that point. That's still going to be a comma f of a. That doesn't change. And it's also p. But then the new point, instead of calling it instead of calling it x, we're going to call it some new point a plus h, where the gap between the two is the h, and so the h is going to grow towards 0. That's what moves. The x in this notation style here, the x is this one. So really it would be a little less confusing if the formula was given in terms of a. So m equals to the limit as h approaches to 0 of f of a plus h minus f of a all over h would, I think, make a little bit more sense, since we'd have the a plus h is this value here. But, a is just a dummy variable. I could have used a, I could have used the letter b, I could have used the letter q. It doesn't matter, right? It's just a dummy variable. And so since we recycle the letter x so often, they go by the letter x. So that's what that means. So for us, in this case, in this particular example, for us, the x is going to be the 1. It's the constant value that we're interested in. Okay? So for us, we're going to have that m is equal to the limit as h approaches to 0 of f of 1 plus h minus f of 1. Right? For us, in this problem, in this little formula, for us, a is equal to 1, or x is equal to 1. Either one, depending on if you're using that formula, or if you want to look at it in this way, or if you want to look at it this way. Either way, this value is a 1. All of it over h. Okay, so now once we have that, now what we have to do is evaluate our function at 1 plus h, and evaluate our function at 1, subtract them, divide by h. Our goal is going to be to simplify this, get it to a point where I can evaluate my function at x equals to 0 and not be dividing by 0. Okay, so remember that our function is 2 over x plus 3. So this is going to be 2 over something plus 3 minus 2 over something plus 3, where this is what goes right in there for the first function, and this is what goes right over there for the second function. So let's put it in there. This is going to be 1 plus h, where this is just 1. And then the whole thing gets divided by h. And we're interested in the limit as h goes to 0. So let me zoom in here while I work on this. And we're interested in this whole thing, m, which is equal to the limit as h goes to 0. Okay, so let's do one more line in here. M equals 2. Okay, so we have one giant fraction where all of this is in the numerator and this is in the denominator. So we can use algebra to rewrite it this way. It makes it a little neater. Instead of dividing by h, I'm going to multiply it by 1 over h. Makes it a little easier to write it down. Okay, multiply it by 1 over h. And then I'm going to rewrite this. All I'm going to do is simplify that. So that's going to be 2 over 4 plus h minus 2 over 4, which then reduces to 1/2. So m equals to the limit as h goes to 0 of 1 over h times this. So to simplify it, bring it under one big happy fraction, we're going to multiply the numerator and denominator of each fraction by the appropriate thing. And the best least common multiple is just to multiply them together. So I'm going to multiply this one by 2 over 2. I'm going to multiply this one by that. So let's erase. And multiply this one by 4 plus h over 4 plus h. And now I'll be able to have two separate fractions that have the exact same denominator. So this will simplify to m equals to the limit as h approaches to 0 of 1 over h times 4 over 2 times 4 plus h minus 4 plus h all over 2 times 4 plus h. So m equals to the limit as h goes to 0 of 1 over h. And then we have 4 minus. Now be careful that this subtraction applies to that entire thing. So I'm going to introduce another parenthesis there to make sure that I distribute it properly. But then we have one big happy fraction with this as the common denominator. So 2, 4 plus h, like that. Okay. Luckily, when I distribute that minus, some stuff will cancel. So we have that m equals to the limit as h approaches to 0 of 1 over h. That'll be 4 minus h all over 8 plus 2h. These 4's cancel. And what I have left over is something. And so now m equals to the limit as h goes to 0 of 1 over h times minus h over 8 plus 2h. And now, finally, these h's cancel. What I have is m equals to the limit as h goes to 0 of negative 1 over 8 plus 2h. And now from our work with limits, we know that the limit of a rational function is equivalent to evaluating that rational function at that point as long as we don't get a divide by 0, which we will not. If we put it h equal to 0, we get just following. So m equals to negative 1/8. That's what we get out of this. Okay, so you have to be really careful with the way you work these guys out. And once we have the slope of the tangent line, then we can use our formula to figure out the equation of the tangent line, because we have the slope is equal to negative 1/8, and we know that it goes through the point 1, 1/2. So using our formula, let's put it over here. Y minus y sub given equals to m times x minus x sub given. We have the formula y minus 1/2 is equal to negative 1/8, comma, x minus 1. So we get y equals to negative 1/8 x plus 1/8 plus 1/2. Common denominator of 8 means we multiply this one by 4 over 4. And so we get y equals to negative 1/8 x plus 5 over 8. And that's the equation of the line tangent at that point. Okay, so find the equation of the line tangent to the function f of x equals to 2 over x plus 3 when x equals to 1. First, we found the output of my function when the input was 1. We saw that that led to the output of 1/2. That's what this was about. And then we used our newfound formula for the slope of the tangent line, which is defined this way. M equals to the limit as h goes to 0 of f of x plus h minus f of x all over h. Right? For us, the x in this case is a 1. So we replace the x with a 1. We get f of 1 plus h minus f of 1 all over h. Then we evaluate our function very carefully. Remember that if we have one giant fraction where the numerator is this whole thing divided by h, well, we can also think of that as a 1, then that's equivalent to 1 over h times the numerator. Good. So multiplying these two things together gives you that one. And it's just a little easier to write it this way as a 1 over h off to the side rather than keeping track of this giant thing with a dividing by h at the bottom. Okay, then you simplify, find a common denominator, reduce, cancel. It's easy to get lost in these equations, but keep in mind that our goal is to get to a point where we do exactly this. Our goal is to get to a point where we can cancel out that h or manipulate our equation in some way so that when I evaluate my rational function at h equals to 0, I will not have a 0 in the denominator. We know from our work with limits that any polynomial or rational function can be evaluated at the value that you're trying to find a limit, in this case 0, as long as you don't result in a 0 in the denominator of a fraction. Okay, so if everything reduced and gave you a polynomial, then great, just plug it in there and that's your answer. If everything reduced and gave you a rational function, then as long as you don't get a 0 in the denominator, you're okay, that's your answer. Okay, so now let's use Desmos to confirm this answer. Okay, so here is my equation, 2 over x plus 3. We know that it has a vertical asymptote at negative 3, so we can graph that. X equals to negative 3. So vertical asymptote is a vertical asymptote. And then we also have a horizontal asymptote at the line y equals to 0 or the x-axis. Okay, and we're interested in knowing what happens when x equals to 1. So when x equals to 1, we get the point 1, 1/2. So that would be this point right there, 1 comma 1/2, that point right there. And we want the tangent line at that point. Okay, so remember the tangent line is going to look like this. Let's have Desmos just generate tangent lines for us. Here is the tangent line. You can see that it looks like that. So we're interested in this one right there. The slope of this line that goes through that point right there. And we think we found it. So let's write down that equation and confirm that it gives it to us. So we found that the equation was equal to y equals to negative 1 divided by 8 x plus parentheses 5 divided by 8. And at least from the graph here, it seems to be confirming it. So the red one is when I simply typed into Desmos, give me the tangent line at that point. And then this purple one is when I explicitly wrote out the equation we found, and they seem to be exactly the same equation. I feel satisfied that that's the tangent line. Okay, so the tangent line moves this way like this at different points. And then the one at that point is that purple one. That's this equation we found. And we can see that, in fact, the tangent line, as it moves and gets right there, it seems to be exactly equal to that. Okay, so we can also say that tangent line has slope. Tangent line has slope equal to negative 1/8, and it goes through the y-intercept at point 0, comma 5/8. Okay, now let's take a look at velocities. So in general, suppose an object moves along a straight line according to an equation of motion s equal to f of t, where s is a displacement, a directed distance of the object from the origin at time t. Okay, so the input value is t, time. It will either be in minutes or seconds or hours, days or years. The most common one we run into is either seconds or minutes or hours, where s is going to be some sort of distance. So it's some sort of equation that describes distance traveled over a time elapsed. The function f that describes the motion is called the position function of the object. In the time interval from t equals to a to t equals to a plus h, the change in position goes from, the change in position is f of a plus h minus f of a, right? It all looks very familiar. And so this is a nice graph that can describe this. So we have an object moving, and so at timestamp a, whatever that is, 5 seconds, 30 seconds, an hour, whatever, timestamp a, it's at this position. And then at timestamp a plus h, you're at this position. You can imagine yourself, say, in a car, and you're traveling in this direction. And then you start at 0. At t equals to 0, we start there. And it's also position 0, the starting line. And then you travel along this direction in your car. And so at timestamp A, you've traveled, from there up to there. That's from f of a. From 0 up to there is the distance f of a. And then if you travel all the way up to here at this timestamp, at timestamp a plus h, then you've traveled from the starting point all the way out to there. So the distance traveled in the time interval between point A, timestamp A, and timestamp A plus h is this distance here, right? So for instance, you start off your car and you're driving, and let's just to pick a number, let's say that this is at 10 seconds. At 10 seconds, you're there, and then you wait a little bit, and then at h equals to 4, that means that this whole timestamp would be 14 seconds, right? The gap is 4 seconds. In those 4 seconds, how far did you travel? Well, that would be the distance f of a plus h minus f of a. That would be described the distance traveled over a time interval of h. Okay, so the average velocity over this time interval, the average velocity is equal to the displacement, the distance traveled over the time elapsed. So the displacement is going to be f of a plus h minus f of a divided by h amount of time. Okay? That'll give you your average velocity. Going back up here. So this red line here will describe the distance traveled, right? So in my little example here, you started at time 0, you started traveling. 10 seconds into it, you've traveled this far, up to there. And then when h equals to 4 at 14 seconds, you've gotten this far. So if we subtract those two distances, the distance from the starting point all the way out to this point, minus, so that would be this blue one here, minus the distance from the starting point up to this point. If we subtract those two, we get this yellow one, the total distance traveled. And in that time interval, 4 seconds elapsed, right? The gap between these two is h. The gap between these two is h seconds, h amount of time. So the average velocity in this time interval is going to be the distance traveled, which is this red part, divided by h. That's what this is pointing out. The average velocity over this time interval is the displacement, which is going to be the subtraction of those two, divided by h. And that's average velocity. So if we had a function, this black one here, that described position, then we can do the same thing as before. We can find the average velocity over an interval and describe it as an approximation of the secant line. So the average velocity over an interval would be equal to the slope of this blue one. The slope of that blue line there is going to be equal to rise over run. It's going to be equal to rise over run of that blue line, which is going to give us this difference right there. That's going to be f of a plus h minus f of a. That'll be that rise, whereas this is h. Okay, so the average velocity would be equal to the slope of that blue line. The average velocity of my object as it traveled between timestamp a and timestamp a plus h is going to be equal to the slope of that blue one. So in my little example from before, we said, okay, let's let this be 10. We said let h equal to 4. Therefore, this whole thing was 14. And so if we found the difference between the distance traveled after 14 seconds minus the distance traveled after 10 seconds, right? This translates into this guy and this guy. This is f of a plus h, or this is f of a. So this, which is equivalent to that, represents the distance traveled in h seconds. Okay, so the slope of the blue one is equal to this, the average velocity in the time interval h. Now, suppose we compute the average velocities over shorter and shorter time intervals, a plus h. In other words, we let h approach 0. We define the velocity or the instantaneous velocity, v of a, at time t equals to a to be the limit of these average velocities. So the velocity, v of a, is equal to the instantaneous rate of change, or the instantaneous velocity, is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h, the exact same equation that we had before. So all we're doing is we're changing the interpretation of the tangent line. In the case where the function equals to a displacement equation, it tells you how an object is changing the distance away from a particular point as a function of time. Then if we want to find the instantaneous velocity at a point, this is what we will get, right? This was the same formula for the slope of the tangent line. Well, that's going to be the same formula that gives you the velocity at a particular point. Good. So this means that the velocity at time t equals to a is equal to the slope of the tangent line at point P, where P was equal to a comma f of a. Okay, let's take a look at this example. Suppose that a ball is dropped from the upper observation deck of the Empire State Building, 250 feet above the ground. What is the velocity of the ball after 8 seconds? How fast is the ball traveling when it hits the ground? Okay, so what we need to do first is establish a position function, right? An equation where the input is time, how long has it been falling for, and the output is the total distance traveled in that time frame. To do that, we can easily Google. I just went to Wiki and looked up equations for falling bodies, and we see that total distance traveled by an object falling for time t, is equal to this equation. D equals to 1/2 g t squared. T is time, and g is the constant force of gravity. It also describes up here that the force due to gravity is 9.807 meters per second squared. And if we wanted to convert that into feet, that's 32.18 feet per second squared. Okay, so this is the force of gravity, g, and then t equals to time, and then the units have to match, and so since this gravity is given to us in feet per second squared, that means that t has to be in seconds. Okay, so armed with that knowledge, we can come back to our example. So this is a very famous kind of question. So d equals to 1/2 g t squared. Total distance traveled. Distance traveled by a falling object. And this is time. Okay, so we're going to use feet per second. So that's going to be 32.18 feet per second. G equals to 32.18 feet per second squared. So that lets us figure out our position function. Our position function, I'm just going to go to t. So f of t equals to 1/2 times 32.18 times t squared is my position function. So this function will tell you the total distance traveled as a function of t seconds since this object started to fall under the impact of gravity. So input is time in seconds. And the output is total distance traveled. Under the force of gravity. Under the force of gravity. Of course, that's on Earth. On Earth, and then of course we're just generalizing this. It varies. Of course, the impact of gravity depends on exactly where you are on the planet. If you're at the top of a very tall mountain, or if you're in the depths of a deep valley, the impact's going to be a little bit different. And there's a lot of cool word problems out there where they maybe talk about dropping a ball on Mars. If you're standing on Mars, for example, gravity's a little bit different versus, an asteroid or something. Or on the moon. So we generalize it, and for the purposes of the math, we don't have to be that precise. So this is just an overgeneralization. On average, it's about 32.18 feet per second, and of course, we're also very much ignoring other things like, for example, air, right? Air resistance. Okay, so let's simplify this by just multiplying these two constants. And so I'll just get P of t equals 2. So this is going to be approximately 16.09 t squared. Okay, let's use Desmos to get a sense of what this means. So I'm using the table feature on Desmos. I put 1/2 and then times 32.18 t squared here. So if we put a 0 at 0 seconds, you've traveled 0 distance. If we put a 1 here, it means that 1 squared times 32.18 times 1/2, we get 16.09. It means that after 1 second of falling from the top, say we were looking at the top of the Empire State Building, after 1 second, it will have traveled about 16.09 feet. Okay, after 2 seconds, it will have traveled about 64.36 feet. After 3 seconds and after 4 seconds, okay, so we can start to see the total. Remember, these are the total distance traveled in feet. After 4 seconds of being dropped, the object will have traveled approximately 257.44 feet. We can graph all of these points, and they would look like. Okay, so these ordered pairs indicate that at time 0, the object would have traveled 0 distance, 0 feet, and then 1 second later, the object would have traveled 16.09 feet, and then 2 seconds later, it will have traveled 64 feet, and so on and so forth. Okay, now position, a position function has to be continuous, meaning that an object can't travel from 16 feet all the way to 64 feet without experiencing every single value in between there, right? So this function here can't be limited to just a whole number of values for seconds. We can find every single position along that lands between 1 second and 2 seconds. We can put some decimals in here. So how about 1.1, 1.2, 1.3, 1.4, 1.5, and so on and so forth. Okay, so if we found every single possible value here, we would end up graphing this. Okay, so the graph would look like this. So to be clear, the object is dropping straight down. So it's not like the object is taking on this shape. This parabolic shape does not represent what you see when you see a ball drop that goes straight down. This parabolic shape just represents the position of the object as a function of time. Okay, so now this particular question asked us about what's happening at t equals to 8. So at 8 seconds, the object will have traveled 1,029 feet. So we got to go way, way up here. So let's go way up here. There it is. So after 8 seconds, the object will have traveled 1,029.76 feet total. And as we just saw, when we have a position function, that's what this green one is, we can find the slope of the line tangent at this point to find the velocity. Okay, so let me write that down. So it's going to be that velocity at time t equals to a is equal to the limit as h goes to 0 of p of a plus h minus p of a all over h, where remember p represents the position function. Okay, so the limit. Okay, so then for us, in our particular case, a equals to 8. For us, a equals to 8. So we're interested in the velocity at time 8 seconds, and this is going to be equal to the limit as h goes to 0 of p of 8 plus h minus p of 8 all over h. Okay. So now we just use our function and evaluate it at this point, evaluate at that point, and remember our goal is to figure out what this limit is. And because we're starting off with a rational function, what we want to do is get to a point where if we replace all those h's by a 0, we don't divide by 0. So our goal is to find a way to either cancel out this h or find an algebraic equivalent form of this that will mean that we're not dividing by 0. Right? That's our goal. Okay, so here's my first function, and I'm going to evaluate it at this point. So I'm going to put 8 plus h there. Here's my second function. I'm going to evaluate it at this point, so I'll put an 8 there. Okay, so let's simplify this. I'm going to simplify it by factoring out what they both have in common, and they both have in common this. They have this and this. Remember, it's just a number, so I can just multiply that out and get 16.09. And then I can factor that out, and what remains is going to be this squared minus 8 squared. So let me write that down. So after we factored out 16.09 out of each term, now we can FOIL this out and reduce a little bit. Also, I'm going to rewrite this a little bit this way. I'm going to rewrite the h over here and then multiply it times this, which when we FOIL it all out, we'll end up with 8 squared plus 16h plus h squared. Okay, so now these cancel. The 8 squared and the minus 8 squared cancel, leaving just these two terms. Okay, so now one of those h's can factor out and reduce with this h. Okay, so this h cancels out with that h. Now when I distribute, and so finally, this is a polynomial, and we know that when we want to find the limit of a polynomial, we can just evaluate the polynomial, and that's equal to the limit. Right? So that's because this is a polynomial. We know our work from limits lets us know that this is equivalent just to evaluating the polynomial at that point. So if we put the 0 there, h, 0 times anything is 0, so the final answer here is just that v of 8 is equal to 257.44, and we know that this is feet per second. Okay, so we have the answer to part A. What is the velocity of the ball after 8 seconds? Okay, so we set up our differential. We found the limit as h goes to 0, and we already defined it. So the ball is traveling at 257.44 feet per second at 8 seconds. 8 seconds after you drop the ball, that's how fast it's traveling. We know that it has traveled a total of 1,000. Let's go back to Desmos. We know it after 8 seconds, it has traveled a total of 1,029 feet. 1,029.76 feet is the total distance traveled from the top when you let go of the object. That's how far it's traveled down. And we know that at this particular point, it's traveling at 257.44 feet per second. Okay, so that's the answer to part A. Part B says, how fast is the ball traveling when it hits the ground? Okay, so the key here is to figure out, well, when is it going to hit the ground, right? How much time does it take to hit the ground? So to answer part B, so this is all part A. Part A. So to answer part B, you first have to figure out when is it going to hit the ground. Well, we know that the whole thing is 1,250 feet, so when it has traveled 1,250 feet, that's when it hits the ground. And this is the position function, so we're going to have to set that position function equal to 1,250 feet and solve for t. So set 1,250 equal to the position function. Okay, so rounding, I'm getting approximately 8.8141. And of course, when you take the even root of both sides of this equal sign, we know there's going to be two solutions. There's a plus and a minus. But in the context of this word problem, it doesn't make sense to have a minus, right? So we get to ignore the minus. So we can check our work. If we look at the position function, means that if we type in this 8.8141, approximately 8.8141 seconds, into this equation, we should get approximately equal to 1250. And it does work out. So what we have now is that after you drop the object, it takes 8.8141 seconds for this object to travel 1,250 feet. And since we know that's the top of the Empire State Building where this object was dropped, that means that that's the point when it hits the ground. It has traveled the entire distance of the building. So now the question wasn't, how long does it take to hit the ground? The question was, what's the velocity right when it impacts the ground? Okay, well, that means we got to come back to this, right? The velocity, but instead of an 8 here, we got to figure it out when it's 8.8141. So we're going to set up this. So then when the velocity is equal to 8.8141, we want the limit as h goes to 0 of this, the position function at 8.841 plus h, minus the position function at 8.841 all over h, which is exactly the same setup we had just a minute ago when we just had 8. Let's go back to the bigger picture here. So this is exactly what we set up here, except here we just had an 8. Now we have an 8.841. So we could do all of this work, repeat it all, except this time with a different number. Okay, perfectly okay. But there could be a part C that says now figure it out when t is equal to 6 seconds, and then you'd have to redo the whole thing. And then there might be another thing that says figure it all out when t equals to 1.72 seconds, right? So rather than recycle the same work over and over and over for different time values, why don't we come back over here and redo this whole thing with an abstract value. Let's leave t equals to a as a variable and solve the whole thing as a function of a, and then we'll have an equation of the velocity as a function of a, and then we can come back and plug in when a equals to 8 seconds or when a equals to 8.8141 seconds or anything else, and it'll make life a lot easier. Okay, so I'm going to erase all of this work here, and I'm just going to replace it all with an a and leave it as a variable, and then at the very end we'll replace the a with the 8, and we'll see that we'll get the exact same answer, and then we'll be able to replace the a with this new time stamp of 8.8141, and we'll see we'll get our answer in a much easier way. Okay, so I'm going to erase a bunch of stuff here. Okay, so we want to leave this alone. Leave it as a variable and solve it that way. So that means that v of a equals to the limit as h goes to 0. And I'm going to pull that h out in front and be 1 over h times all of this. So that'll be p of a plus h minus p of a. Okay, so that means that v of a equals to the limit as h goes to 0 of 1 over h times, and now our position function, remember that one was just 1/2. So for this first one, we're going to put a plus h there. For this next function, we're going to put the a from there. Okay, so 1/2 times 32.18 is just the 16.09. Same thing there. So now I'm going to write this on the outside, factor it out, and I'll just have this squared minus this squared. Then becomes 1/h times 16.09 times a squared minus 2ah minus h squared, plus, that's foiling this out, minus an a squared. Then the a squares cancel, giving me 1/h times 16.09 2ah plus h squared. Finally, one of those h's can factor out, and then we'll cancel with this one. So we'll have 16.09 all over h times 2a plus h squared. Then this h reduces with that, and what we have left over is so when we distribute, we'll end up with 3218a plus 1609h. And now, finally, this is a polynomial. So we know we can just evaluate it at that value and get our result. Okay, so V of A equals to 32.18a. And so now, finally, for the specific case of A equals to 8, so we'll put when A equals to 8, all we have to do is replace that A with an 8. And we get V of 8 equals to 32.18 times 8. And we get the exact same answer, 257.44 feet per second. Okay, but the valuable thing here is that now we have a nice little equation, and we can easily find the value at any time interval, timestamp A, where now in this case, we wouldn't have to repeat that whole limit and figure out the limit of this, right? Instead of all that work, I can say now, let's just use this formula. And so this formula says to find the velocity when we have 8.8141, that's equal to 32.18 times 8.8141. And we arrive at 6377 feet per second. Okay, just a quick recap then. A ball was dropped from the top of the Empire State Building. We are told that it is 1,250 feet above the ground. This is a standard equation that always works for any object being dropped on Earth. When we simplify it, approximate it, ignore lots of other little details, but you'll see in lots of your classes, this is the equation we work with. So this is in feet per second. There's also very popular meters per second, so be careful what units you're working with. Okay, so this is a position function. When we input various values of t, how long it's been since you let it go, this function will tell you the total distance traveled. Okay, so part A, we wanted to know what is the velocity after 8 seconds. So if we set up our equation, the velocity at t equals to a, we get this. So we can replace the a with an 8 right now and then solve it. We did that, and we got an answer of 257.44 feet per second. Part B said, okay, well, how fast is it traveling when it hits the ground? So the first thing you need to do is decide, well, how long is it going to take for this object to hit the ground? So we take our position function and we set it equal to 1,250 feet because that's how tall the building is. And then we solve for t. We ignore the negative. We got that it would take 8.8141 seconds approximately for it to hit the ground. And once we have the value of t, how long it's going to take, we know that it's going to travel 1,250 feet in that time. And what's the velocity? Well, we could set this whole thing up one more time and solve the whole thing. But then hopefully that triggers the idea that it just makes more sense to solve this in general. Leave the a as a variable and solve it in general. So we did that. We came back over here, solved it for a. We got an equation. So this is a velocity equation as a function of a, where a is a time stamp. How long since you initially let the object drop, right? So we can come back and solve part a really easily. We can just replace the a with an 8 and get the same answer. And now we can solve part b really easily. We can just take this function, replace the a by an 8.8141, and we get our answer. So the ball, after 8 seconds, it has traveled. Let's go back to this function. So we know that after 8 seconds, it has traveled 1,029 feet, and we know that it's traveling at 257 feet per second. And now we know that if we go 8.8141, we travel approximately 1,250 feet. That's this one right there, approximately that much. And we know that we will be traveling at 283.6377 feet per second at the point of impact. Okay, so a recurring theme should begin to present itself, because just earlier when we were looking at the slope of a line tangent to a point of a function, we use this exact same limit. The exact same limit presents itself. So a second interpretation of this is to say that when we look at the slope tangent to a point on the position function, the slope of that line is the velocity. Okay, so on a graph, so we go back to our graph. This parabola represents the position function. We know that the horizontal axis is time. So at t equals to about 8.814-ish, it has traveled a total of the object has traveled a total of 1,250 feet. And then at 8 seconds there, it had traveled a total of 1,029 feet. But also want to know about the velocity. So we found the velocities by using our formula for velocity, but it's the exact same formula that is equal to the slope of the line that's tangent. So if we look at the line that's tangent, it looks like this. This red one is the tangent line. Zoom out just a little bit. So this red line is the tangent line at this point. And if we found the slope of the line, the slope of this tangent line, it would be this. So let's just have Desmos calculate for us. So here I'm asking Desmos just to calculate the slope of that line, and we get that, the velocity. So the slope of the line tangent at a point on the position function is equal to the velocity function. Good. Same thing right up here when we let a equal to approximately 8.814. We know that it's traveled a total of 1,250 feet. And if we get the slope of the line tangent at that point, that is going to be the 283.63, the velocity at that point. Okay, so finally we arrive at our formal definition of derivatives. So as we have seen, this type of a limit appears whenever we're trying to find the slope of a line that's tangent at a point. And also, the exact same limit presents itself when we're looking at the velocity problem, right? The velocity when we're given a position function. Okay, there's lots of places we're going to run into this thing. Whenever we're looking at the rate of change of something in any one of our sciences or engineering classes, we'll see that this same limit presents itself. Very popular, so popular in fact that we give it a specific name. That's what derivatives are. So here's our formal presentation of the derivative. So the derivative of a function f at a number a denoted by f prime of a. So it's going to be this little tick mark thing here, prime of a, is this. F prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h, right? And one interpretation of this is exactly like we saw with the tangent. This is going to be an equation, right? Once we figure out this limit, if it exists, it'll be an equation that gives us the slope of the line tangent at a point A, right? It's an equation that's going to be a function of A, if it exists. Now, if we change our notation, right? This is using the notation of x equals to a plus h. On the other hand, if we want to go back to our notation of letting point A be the one we're interested in and letting some other point just be x, then we can go back to this notation as well. Right, so we've seen how we can go back and forth between the two. Okay, so at the start of this video, we were looking at tangent lines, and we went through this whole thing about finding a limit that would help us find the slope of the tangent line. Well, we just saw that it's exactly the same thing as this derivative, f prime, so we can bring those things together and be able to say that the line to y equals to f of x at point a comma f of a is the line through the point a comma f of a whose slope is equal to f prime of a. Since the derivative at a is going to be the exact same thing as the limit definition that we went through earlier. Okay, so find the derivative of f of x equal to 3 over the square root of 1 plus x at x equals to a. So using our definition, f prime of a will be the derivative, which is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. Okay, so our function is this one. So we get that f prime of a is equal to the limit as h goes to 0 of, okay, so it's going to be our function evaluated at a plus h minus our function evaluated at a, and then the whole thing divided by h. Okay, so we have one giant fraction divided by h, so I'm just going to rewrite it this way. Okay, so to simplify this, I'm going to multiply the numerator and denominator of both fractions by something that will give us the appropriate value. So I'm going to multiply this fraction, numerator and denominator, by 1 plus the square root of 1 over the square root of 1 plus a. This is a new version of 1, so I haven't changed my fraction. And then this one I'm going to multiply by 1 plus a plus h, square root of that, all over 1 plus a plus h, square root of that. Now, both sets of fractions are going to have the exact same denominator, so I just have to simplify the numerator. Okay, so I'm going to factor out a 3 and rewrite this whole ugly fraction. So I'll end up with 3 divided by h multiplied by the square root of 1 plus a minus the square root of 1 plus a plus h, all of it over this very ugly denominator, which is going to be the square root of 1 plus a plus h times the square root of 1 plus a. Okay, we're almost there, except that we still have a problem. If we try and evaluate this whole thing at h equals to 0, we're still going to be dividing by 0. We got to get to a point where we factor, cancel, or reduce this somehow so that we don't have that problem. And unfortunately, the next thing we have to do is to now complicate our life a little bit more by multiplying the numerator and denominator by the conjugate of this so that we can take advantage of our difference of squares property. So we're going to multiply the numerator and denominator by 1 plus a, square root of that, plus the square root of 1 plus a plus h, divided by the square root of 1 plus a plus square root of 1 plus a plus h. So first of all, we're allowed to do this because this is a new version of 1, right? Just like these, they're all 1, so we haven't really changed our fraction. But the advantage is going to be that when we multiply these things out, the numerator is this binomial times this binomial, and they're conjugates of each other. So we know from algebra, recall from algebra, that if we have a plus b times a minus b, they're identical in every way, shape, and form except this has a plus, this has a minus. When we FOIL them out, we'll end up with a squared minus ab plus ab minus b squared. The middle terms then cancel out, and what we have left over is just the a squared minus the b squared, right? So when we have binomials like this, where one of them is a plus and the other one is a minus, everything else is identical, after we FOIL everything out, we'll end up with a squared minus b squared. Well, that's what we have here. We have this, which is identical to this one, and everything's the same except one has a minus, one has a plus. So based on this property, I know that when I FOIL them all out, it's really just going to be this term squared minus this term squared, right? It doesn't matter what the order is. One's plus, one's a minus. It doesn't matter. We'll always end up with a subtraction there. So based on that, I can say that this is going to be I can tell that the product of these two binomials is just going to be this. The first term squared minus the second term squared. And the denominator, well, let's leave it alone. Let's not worry about it. It's going to be very ugly. It's just going to be the multiplication of everything. I'm not even going to try and simplify it. So it's going to be this square root of this times the square root of 1 plus a times, and now we have this little addition of 1 plus a plus the square root of 1 plus a plus h. And yeah, maybe we could try and simplify it a little bit, but it's not necessary. I don't think it's worth the trouble. Okay, well, what's great here is that now the square root and then squared, these two operations are inverse operations. They undo each other. So the fact that we have the square root and the squared is going to cancel out. We end up with just the 1 plus a in the numerator. And same thing over here. Something that's square rooted being squared, this operation and that operation undo each other, liberating whatever's inside there. So let's copy that down. Okay, so now if we distribute, make sure we distribute this sign across there, and we end up with the following. And so now a bunch of stuff will reduce. This reduces with that guy, and this guy reduces with that guy, leaving me just a minus h in the numerator. Finally, this h will reduce with that h, giving me just a minus. Okay, well, initially it might seem that I took a perfectly nice, innocent looking fraction and made it even more complicated, which I kind of did. But the advantage here is that we were able to cancel out these two h's, meaning that this resulting very ugly rational function does not equal to 0 when we evaluate it at h equals to 0, right? We're not dividing by 0 when h equals to 0. So because of that, we get to just find the limit by evaluating it at h equals to 0. So that means that f prime of a is going to be equal to I'm going to replace all those h's with a 0. 0 there from that h, and a 0 there from that h, and then simplify it a little bit. Okay, so because this is a 0 here, we end up with a 1 plus a times a 1 plus a. When we multiply these two, the roots are going to disappear. We're just going to be left with a 1 plus a there. And then these two are identical, so it's going to be twice these. So f prime of a equals to 1 plus a times twice the square root of 1 plus a in the denominator, and then a minus 3 up in the numerator. So we can simplify this just a little bit more by rewriting it this way. It's customary to put the constant out in front, so I'm going to rewrite it as a. And there's our final answer. Okay, so a very popular question to ask is to find the derivative of a function at x equals to a, just an abstract variable. So we set up our limit, follow our definition of derivatives, and then be very careful about following the instructions of your function and evaluating it at a plus h first minus f of a all over h. Remember that once you get it to this point, your goal is going to be to manipulate it, use algebra to cancel, reduce, find some way to change it into a new form, equivalent to a new form that allows us to evaluate this function at h equals to 0 and not be dividing by 0. If I did that right now, if I replaced the h with a 0, I would be dividing by 0. Same here, right? As long as I have this 1 over h out in front, I'm going to be dividing by 0. We know that's not allowed. So if we get to a point where we can manipulate it and get to this stage, see here the h's cancel, then we've achieved our goal, because at that point, we have a limit of a rational function, and we know from our work with limits that when you have a rational function, you're trying to find the limit, it's equivalent to just plugging that value in. The limit as h goes to 0 of a rational function is equal to the value of the rational function at h equals to 0 as long as you're not dividing by 0, which we've accomplished here. So at this stage, we can just replace the h's with a 0, and then things work out nicely after that, and we simplify. So the next natural question you must be dying to ask right now is, do we have to do it this way? And the answer is yes, you do have to do it this way right now. This is finding the derivative by the definition. So when our test comes along, the question will say, find the derivative using the definition of a derivative, which means that this is what I want. Okay, so make sure you practice this on your homework, that you have to do it like this. Be very clean and neat. The trick needed isn't always the same. So here I had to bring these two together, so these two different fractions together as one big happy fraction, so I need to find a common denominator, and then the trick was to multiply the numerator and denominator by the conjugate of the numerator. Every question is a little bit different, so there's different algebraic tricks you might need in order to be able to manipulate this and get it to a point where we solve the limit. Okay, so be very neat, be very clean about this, and find your derivative this way. As we move forward, we will be looking for shortcuts, right? Finding shortcuts is a big part of calculus, so we will definitely be using shortcuts in the future. We won't always do it this way because, as you can see, this is painful. Even for a relatively easy equation like this one, it was still a lot of work, right? So we will be looking for shortcuts in the next chapter, but for now, We are not allowed to use any of those. So if you've already had calculus in the past and you already know, some of the secrets that are coming our way, then that's fine. You just can't use them right now. On this first test, when I'm testing chapter 2, you're not supposed to know any of those shortcuts, so you won't get any credit if you find the answer by doing it in a easier way. Okay, so you got to use the definition, follow this process, write it all out really nice and neat, and get to your derivative. Okay. One more thing, keep in mind that a is a dummy variable. It's at x equals to a. I like to use it because I think it makes it easier, I think, to see that we're capturing at a particular point. But I could have used, instead of a, we could have used b, replaced all the a values with b. We would have ended up with a function of b. We could have used w, we could have used m, we could have used any letter. So, being that mathematicians are so in love with the letter x, very often we just let the variable be x, right? It's a dummy variable. It could be a, could be q, could be m. Why not let it be x? So keep that in mind, that when you look at your book, very often, if you look at solutions, they just leave this as an x. So you'll end up with f prime of x instead of f prime of a. Okay, same thing. Okay, so now find the equation of the tangent line to f of x equals to 3 over the square root of 1 plus x at x equals to 15. All right, well, luckily we've already figured out the derivative at a, right? So from before, when x equals to a, we did it in general, we found that this was our setup. It's equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. And we did a bunch of work, and then we found that the derivative of a was equal to -3 all over twice 1 plus a times the square root of 1 plus a. Okay, so we can evaluate this when a equals to 15. Now, when x equals to 15, we have two ordered pairs. First of all, let's find the ordered pair on the function. So that'll be blank equals to 3 over 1 plus blank square rooted. And I'm going to put in a 15 here and a 15 here. Okay, so that's a nice convenient result. That turns out to be 3 divided by the square root of 16, which equals to 3/4. Okay, so we have the ordered pair 15 comma 3/4. 15 comma 3/4 is a point on my function, and I need to know the slope of the line tangent at this point. Well, luckily, we have this nice equation right here. So now, f prime of 15 is going to be equal to -3 over 2 times 1 plus blank times 1 plus blank square rooted. And this is where we get to insert the 15 in there, 15 in there, 15 in there. So we'll get that this is equivalent to -3 divided by 2 times 16 times 4, which is going to be equal to 32 -3 divided by 4 is going to be 128. 128. Okay, so the equation of the line tangent to this function at this point, well, we found the actual point right here. This is the ordered pair of our function. So we have one point on the tangent line, the point where the tangent line is going to touch our function, and then we know that the derivative is the slope of the line tangent at that point, so that means it's got this derivative. So we can bring those two things together and now say that the tangent line will have the following equation. going to be y minus 3/4 is equal to negative 3 over 128 x minus 15. Okay, so distribute. Okay, so we get our final equation as y equals to negative 3 over 128x plus 141 divided by 128. Okay, so that is the equation of the line tangent at this point. Okay, rates of change. So suppose y is a quantity that depends on another quantity x. Thus, y is a function of x, and we write y equals to f of x. If x changes from x sub 1 to x sub 2, then the change in x, also called the increment in x, is delta x. So this little triangle, we read it as delta x, or the change in. It represents the change in x. So change in x, delta x, is equal to x sub 2 minus x sub 1. Okay, so the x value changes from x sub 1 to x sub 2, so the change in x is this difference. And the corresponding change in y is going to be delta y, again, change in y, equals to f of x sub 2 minus f of x sub 1. Looks pretty familiar, right? So here's a nice picture to describe this exact same situation. We have some sort of a function. That would be this black one here. This is some function f of x. This black one establishes a relationship between an input value x and an output value y. So y as a function of x. So if an input value changes from x sub 1 to x sub 2, then the change that occurs is this little delta x. And if that change happens from x sub 1 to x sub 2, then the corresponding change in its output will change from f of x sub 2 minus f of x sub 1, which is this delta y. Exactly the same thing we've been doing over and over and over again, right? So this is just really driving home that there are lots of different ways of looking at the exact same thing. Okay, so now if this delta x change occurs, right? So we get this change occurs in the x axis direction, and then as a result, we get this change in the y. Then we can divide these two things to get the average rate of change over this interval, right? Which is what this is. The average rate of change will be the change in the y divided by the change in the x, very similar to the slope we've been working with so far. So, as you might guess, what we want to think about is what happens as we make that interval get smaller and smaller and smaller. So by analogy with velocity, we consider the average rate of change over smaller and smaller intervals and let x sub 2 approach x sub 1, just like we've been doing already before. So as we let delta x approach 0, we end up with the following. So the limit of these average rates as change is called the instantaneous rate of change of y with respect to x at x equals to x sub 1, which, as the case of velocity, is interpreted as the slope of the tangent line to the curve y equals to f of x at point P equal to x sub 1 comma f of x sub 1. Okay, so it should all look familiar at this point. The instantaneous rate of change is equal to the limit as delta x approaches 0 of delta y over delta x. And when we figure out, well, how do we interpret delta y, that's the change in the y-axis direction. That's going to be the difference of these two values. And when we figure out, well, what's delta x? Well, that's the difference of these two values. It looks exactly the way we've seen it before. This is the derivative, right? We recognize this as the derivative f prime of x sub 1. So we know that one interpretation of the derivative f prime of a is the slope of the line tangent to the line, tangent line to the curve y equals to f of x when x equals to a. We now have a second interpretation. The derivative of f prime of a is the instantaneous rate of change of the function y equals to f of x with respect to x when x equals to a. So two ways of looking at the exact same thing. What is derivative? Okay, the derivative can be interpreted as the slope of the line tangent to a particular point. Okay, when you're thinking about a function that's the position function, the derivative of the position function will give you the velocity. That's another way to look at it. And in a more general way, whenever you're given some function f of x, then the derivative can be thought of as the instantaneous rate of change of our function at that point. Okay, so I think that should be more than enough to try out the homework. As I said earlier, make sure that you practice using the definitions, the definition of derivative, to find your answers. I know many of you guys are well aware of some of the awesome shortcuts that are coming our way, but we're not allowed to use them yet, right? So we're pretending you don't know them yet. We have to do it by the definition. So you have to set up the limit, and then you have to solve it based on the rules of limits that we've learned so far. Okay, so try out your homework and let me know if you have any problems, issues, or concerns.